Welcome to another physics video. Our topic today is parallel electric circuits. A parallel electric circuit is one which provides more than one path for current to follow. We'll have to look at a diagram to see how this works. As we've seen in our series circuit video, every circuit must contain a battery. The two parallel lines represent the battery, with the longer line being the positive side. This means that current will flow in a clockwise direction in this circuit. The blue arrows represent the current. We also want a device in the circuit that can use the energy provided by the battery. We can represent any device by its resistance value. The symbol is a rectangle. Since this circuit only contains one device, all of the energy, voltage, provided by the battery is used by the one device. Now, let's add a second device by adding a second path in the circuit. The original path is shown in blue and the new path is shown in red. We draw the circuit this way for convenience. By adding a second path, we have increased the current leaving the battery. In this case it has doubled because both resistors have the same value. Here's the original circuit. Notice that the current through R1 is 2 amps. In the new circuit, R1 still gets 2 amps, but there are 2 additional amps going to R2. This means there is a total of 4 amps leaving the battery. We can say that the blue line represents the current for R1 and the red line is the current for R2. Near the battery, we have both the blue and red lines, so we have more current. This is an important feature of parallel paths. Each time we add one, the current from the battery increases. This also means the equivalent circuit resistance decreases. To understand why this happens, let's look at a different version of this picture. I have identified 2 points in the circuit, A and B. We will use these points for determining voltage differences. There are 3 different ways to get from point B to point A. These are the 3 different colored paths. The red path goes from point B, through the battery, and then on to point A. This path has a voltage difference equal to the battery. In this case, it is 20 volts. Any other path from B to A should have the same voltage difference, because they are always the same 2 points in the circuit. The blue path takes us from point B, through R1, and then on to point A. This path represents the voltage difference across R1. Because we are still going from B to A, the voltage difference is still 20 volts, just like for the red path. How about the green path? Again, we start at point B and end up at point A, but this time we pass through R2. Since this path has the same starting and ending points, it has the same 20-volt difference. This means there is a 20-volt difference across R2. It is because these paths all have the same voltage difference that we call them parallel paths. Point A and B are called junction points in the circuit. At these points current will either split, like at point B, or join together, like at point A. At point B, the red line arriving represents the total battery current of 4 amps. Notice that the green line shows 2 amps leaving and the blue line shows 2 amps leaving. This shows the other feature of parallel paths in a circuit. The current splits, it divides itself between the different paths. Let's summarize what we've learned. The term parallel tells us that there will be more than one path for current to follow through the circuit. Each time we add a new path in parallel, the current leaving the battery will increase. However, the current in the old paths will not change. The current from the battery will divide between the parallel paths. However, the voltage difference will be the same for all parallel paths. In series circuits, current is the same everywhere and voltage divides between the devices. However, in parallel circuits it is reversed. For parallel circuits, it is the current that divides and the voltage is the same for each path. We saw that since adding more parallel paths increases the current from the battery, the equivalent resistance has to decrease. Here is how to calculate the equivalent resistance for parallel paths. Notice this is more complicated than when the resistors are in series. This is a two-part equation. First, add the reciprocals of each resistance value. This is the right-hand side of the equation. But, looking at the left-hand side, this equation tells us how to find 1 over equivalent R, and we want to know the equivalent R. So, after we add the reciprocals of the resistances, we need to find the reciprocal of the answer to determine the equivalent resistance. That's the parallel circuit story. Goodbye until the next video topic.